So in my degree, I learned how to solve equations, but I didn't always understand what those equations meant or what they were telling me. But secretly, I wanted to study earth science. So after my undergrad, I headed to an earth science department, and actually now I'm in a geography department. And I've learned a lot through being in these different departments, and mainly through talking to a massive range of different people. So the list of people here in my acknowledgements, they come from geodynamic modelling, glacial geology, geodesy, ice sheet modelling, seismology. Really a massive wealth of information has gone into this, and a lot of credit to those people who guided me so far through my career. And actually sitting in a geography department, also an earth science department, I was introduced to data for the first time after my undergrad degree. And that's quite unnerving for a mathematician, because I was used to things being right or wrong. So actually dealing with uncertainty, trying to tease out what those data can tell me, has been a massive part of my career so far. To the degree that I've very luckily gone from sitting behind a computer solving equations to sometimes actually heading to Antarctica, which is my area of interest. So this was my office for a day back in February earlier this year. We were installing, there's a GPS receiver just off to the right of this shot here, and we also installed a seismometer which is buried in the moraine up here. They're out there now, and I'm going back to look at the measurements that I'm making. And towards the end of the talk you'll see how those measurements sort of play into the modelling that I do. So this is the Bullerwell Lecture. And William Bullerwell actually probably made all my research possible. So this is a quote from his obituary looking at his career. And he really made a massive jump in sort of traditional geological studies to using geophysics to understand things. And this is absolutely crucial in Antarctica. We have a massive ice sheet in the way. And I need to know what's going on underneath the ice sheet. I need to know the geology. I need to know the thickness of the lithosphere and the properties of the mantle. I need to know if there's water at the bed between the ice and the solid earth. And geophysics has really made this all possible. So it's actually really, really fitting that this is the Bullerwell Lecture. So as Mark mentioned, the field that I've worked in since the start of my postdocing is glacial isostatic adjustment. I will refer to it as GIA from now on. It's a little bit less of a mouthful. And I look back at the abstract I submitted, and this is what I'd written. It tackles the classic geodynamical problem of determining the solid earth response to surface load changes by ice and water. And that's really the nub of what I'm trying to get at is to understand the solid earth, but also to understand the ice sheets. It's really quite a coupled problem that I'm looking at. So traditionally what we do when we run a geodynamical model, we have some idea of the history of the ice sheet, how thick it was, how big it was. And we place it on the solid earth and look at the deformation of the solid earth. And we calculate the deformation of the whole of the solid earth. And the reason for that is because as an ice sheet melts, that water has to go somewhere and it goes into the ocean. So in my models, I not only model the shape of the ice sheet, but I also model that redistribution of meltwater across the ocean. Now, if there was no physics, no gravitation, no rotation, the ocean would just be a nice sphere and sea level would go up and down uniformly. But actually the ocean follows the shape of the geoid, so there's a sort of emphasized shape of the geoid image down here. And what we have to think about as we sort of think about the meltwater and where it goes into the ocean is we have to distribute it gravitationally consistently. So this is one of the equations we solve. We solve for the shape of the geoid as we run through time. And that tells us where this ocean water goes. Now the ocean water also acts as a surface load. So you can see there's a little bit of complication here. It's not just we have to actually iterate the model. So we think about how the ice sheet changes, how the earth deforms, and we throw that in the ocean in quite a simple way. But then we think about, hang on, how is the earth deformed because of the ocean water? And we iterate and think about the change in the shape of the gravitational field due to all of these surface masses moving around. So I'm going to give you a little bit of a, sort of the next 10-15 minutes is going to be a motivation of why I study GIA. We've got a very mixed audience here, quite a technical audience, but hopefully there'll be something in each of these three components that you'll find interesting. I think GIA is interesting to everybody, but I am a little bit biased. So I'm going to start, I'll talk about these three components in turn. I think a lot of you are concerned with the solid earth. And the sort of questions we're asking when we run a GIA model is about the rheology of the Earth. How does it deform? We can actually look at different depths within the solid Earth because we have small ice sheets which excite deformation at quite shallow depths. And we also have massive ice sheets that cover Antarctica today and North America in the past. And they actually excite deformation very deep inside the mantle. And as we look at that deformation, we can start to understand the rheology of what's going on down there. And we also get to think about very, very different timescales. I was in an earth science department for a time, and time moves slowly in an earth science department. Geological timescales slightly unnerved me, but once we come to GIA, we get to think about, well, okay, thousands of years. I can sort of grasp thousands of years. As we move ice around, we can see the sea level changing today. We can measure the solid Earth responding and changing shape in response to these changes. So I get to look at a bunch of different timescales, which makes me a little bit happy about what my understanding is. So that's thinking about what we can learn about the Earth. We can actually learn about the ice sheets via this process. So traditionally what we do is we come up with some idea of how the ice sheets change through time and look at the sort of deformation. But we don't actually know how the ice sheets changed through time. So we actually have to sort of back calculate this out of the observations that we have. So the most sort of the easiest way to visualize this is to look at vertical uplift in the present day. So this is a map of Scandinavia. Here we have the Fennoscandian Peninsula here, Finland over here. And the dots you see here, the colors of the dots don't refer to anything. They're locations of GPS receivers. And this coloured surface, it's an interpolation of the uplift rates measured at these GPS receivers. And this network's been running since the mid-90s, so we've got a very good velocity field across here now. And you can see in the centre of Scandinavia, we have these uplift rates of over 1 centimetre a year going on right now. And so this gives us a nice sort of picture, a paleo picture of what the ice sheet looked like. Perhaps there's the thickest ice here, and it pushed the Earth down, and it's now rebounding very, very quickly. You can also see this in the horizontal field of the GPS data. You see this beautiful outward profile of rebound. So we can learn about the history of the ice sheets by working out what loading history would give us this present day deformation field. Now that's fine where we don't have an ice sheet anymore. But my area of study, which is Antarctica and also Greenland, we still have an ice sheet. And this causes a lot of problems because these ice sheets are changing right now. So the ice sheets were both larger during the last glacial maximum, about 20,000 years ago. So we have this relict rebound from the larger ice sheet, but we also have deformation going on right now because those ice sheets are changing mass. So my job is really to tease apart the sort of the past and present signals of rebound across these ice sheets to really get a picture of how they're changing right now. And what we always do is we then link this back to think about climate forcing. We have very good paleo records of climate over the time periods that I'm interested in, which is sort of a glacial cycle, a couple of glacial cycles. And if we can look at how the ice sheets change and how the climate changed, we can start to think about how those ice sheets might respond to future changes. Now the third colour in this diagram here is the ocean. And a big question posed to society right now is how is sea level changing? What's driving that sea level change? Now, there's two reasons sea level changing, very, very naively. We're adding mass to the ocean from an ice sheet melting, going into the ocean, and we're also expanding the ocean as we change the thermal content of the ocean. But actually, as we add some meltwater into the ocean, as I mentioned earlier, it doesn't just rise or fall in a uniform way. And it's important to understand that as we look at measurements of present-day sea level change around the world. So this is a map of ongoing post-glacial rebound. So this is a solid Earth deformation across the world. So this is in millimetres per year, due to the past ice sheets, how they've changed. So you can see these red areas across Scandinavia, the Barents Sea, North America, and Antarctica, where we had much larger ice sheets in the past. And this is a model prediction guided by measurements of the present-day uplift rates. Now you can imagine, one of the ways we measure sea level change is a tide gauge which sits on the solid Earth and measures how the sea level changes relative to solid Earth. Now if your solid Earth is moving up very quickly, you're not going to measure mean sea level change that's relevant across the world. So for example in Scandinavia, the rate of rebound there is so large that communities have had to move over the centuries. So sort of on a time scale of a lifespan, the sea level can change up towards sort of 50 centimetres, 60 centimetres because of the rebound. So they really noticed sea level change in Scandinavia, but they thought sea level was falling because the land is going upwards. Whereas actually we know from the last thousands of years, sea level's been rising as we've been warming the oceans and melting the ice sheets. So we account for these, the solid earth deformation at the tide gauges to try and actually take out the GIA component and look at sea level change across the ocean. We also, one of the questions that we're asked very often is how quickly might sea level rise in the future? And what we do again is we look back to the paleo records and we ask the question of how quickly has it risen in the past? And most importantly, where did that meltwater come from? Do we have ice sheets in some sort of unstable configuration that they could deliver a lot of meltwater very quickly? What were those conditions and how quickly did they deliver the meltwater? And to explain this, I'm going to go to some fingerprint plots. So these might be new to a lot of you. What these are showing, these are normalized plots. And basically the figures showing the rate of sea level rise that you would expect around the world if you had a meltwater input from either the North American ice sheet or the West Antarctic ice sheet. And you can think of this, if we add some units, it's non-dimensionalized, but if we added units, it's as if it's rising, that the meltwater would rise sea level by 1 millimeter per year. Now, without physics, without rotation, without gravitation, you'd see this sort of yellow-blue transition everywhere, sea level rising at 1 millimeter per year. But actually, this is a model prediction. Actually, this is what we observe as well with contemporary sea level change. We see these patterns. Is that you go from sea level rise at about 1 millimeter per year along this yellow-blue transition to actually sea level rise at rates faster than the meltwater has been delivered, and also sea level fall close to the ice sheets. And this is quite a surprising result, but there's a neat little figure which explains it. So if we have this ice sheet on the left here, the ice sheet is very massive. It actually attracts the ocean towards it. So this is an exaggerated diagram with the ocean surface drawn up towards this large ice sheet. And the ice sheet is also loading the Earth, so the land's pushed down a little bit where the ice sheet exists. Now, if we step forward in time and have a smaller ice sheet, there are two things that happen. As the ice sheet becomes smaller, the land rebounds upwards, so the dashed line is the original position, and the solid line is the new position of the Earth, which rebound upwards. But also the shape of the geoid, the shape of the ocean surface changes. As the ice sheet becomes less massive, it exerts a smaller gravitational attraction on the ocean, and the sea surface flattens in the near field of the ice sheet. So although our net delivery is of meltwater to the ocean, in the far field we will see sea level rise, an increase in water depth. Actually, close to an ice sheet, we'll see a sea level fall. We expect to see a sea level fall due to a drop in both the ocean's surface height and rebound of the solid Earth. So it's quite a counterintuitive situation, but that explains these figures here where the models predict sea level fall close to the source of some meltwater and sea level rise in the far field. So to come back to this question of how quickly did sea level rise in the past, we have some beautiful sea level records from the tropical regions looking at coral records from places like Barbados and Tahiti. Now, there are two main hypotheses about this sort of, so there were big meltwater deliveries during the last deglaciation, where we saw sort of 15 meters of ocean sea level rise in just a few hundred years. And one hypothesis is that the meltwater came from the collapse of the Laurentide ice sheet, the North American ice sheet, and another hypothesis is that it came from West Antarctica. So you can see actually, depending on the source of the meltwater, we would record a very different pattern of sea level rise at these different locations around the world. If the meltwater came from Barbados, we'd actually expect to see a slight fall in sea level. That's actually probably a less than eustatic rise in sea level close to the ice sheet, but a greater than eustatic sea level rise over in Tahiti. So the goal really in sort of sea level studies associated with GIA is to look for a good spatial distribution of sea level records. And if we can understand the different signatures in the sea level change around the world, we can start to piece together the source of sea level change and where that came from. So as we look back into the history of geological records, that's one example of why we might see lots of different variations in sea level. And actually, so one of my favourite features of GIA is these blue areas around here, which are known as peripheral bulges. So we have the ice sheets in the past in these red areas, and now the land is rebounding upwards. But when the ice sheets existed, they pushed the Earth down, and you had a peripheral bulge region around the ice sheets, which was slightly raised upwards. So now the ice sheets have gone. Those areas are now subsiding. They've been subsiding since the ice sheets disappeared, and they're ongoing subsiding. Now these bulge regions are typically in the ocean. So they're around the margins of the ice sheets, which are based on the continents. But if you integrate the rate of solid Earth deformation in the present day across the oceans, you get a net fall in the height of the sea floor. Now what this means is that since the ice sheets sort of disappeared, the Northern Hemisphere ice sheets around 7,000 years ago, our ocean basin has been increasing in capacity. So we had these bulges within the ocean, and they're subsiding. So our bath is actually getting bigger. And what we see around the world is we actually see a high level of sea level around 6,000 years ago, and then sea level fall since then. And that's not due to a change in the volume of the ocean, but it's the change in the shape of the sea floor. As the sea floor subsides, we see this fall in sea level. So that's a fantastic example of how we have to think a little bit carefully every time we look at sea level records. Every time someone comes to me with a sea level record, I start thinking, right, has the Earth deformed? Has the shape of the geoid changed? So actually we see this high stand in sea level in the mid-Holocene, but it's due to change in the shape of the solid Earth, not in the change of the ocean volume. We can look a little bit further back in time as well. This is a plot from a paper by Maureen Ramo thinking about Pliocene sea levels, so about 3 million years ago. People are interested in this period because it's sort of a proxy for where we might be heading under current climate change. So the question is, under sort of the CO2 levels that we're seeing now and we might see in the future, how big will the ice sheets be? So the question is, how high was sea level? Because if we can work out how high sea level was, we know how big the ice sheets were. And there's a lot of sort of geological observations around the world for the height of sea level at this time. And some people might work in South America, and they say, oh, sea level's about 10 meters higher at this time. But then you talk to some people perhaps working down in the Caribbean here, and they say, actually, no, your records are wrong. Sea level was 18 meters higher at this time. And this caused quite a lot of discussion in the paleo sea level community, and there were large error bars placed on these data. So we didn't really have a good idea of how much smaller the ice sheets were and how much higher sea level was. But what this study showed was actually we would expect records of past sea level to be preserved at different elevations in the present day. So what this plot is showing is as if we had melted around 14 meters of equivalent sea level from Antarctica, put it into the ocean, and then they run the model forward through time for 3 million years and think about where would those shorelines be today. And it turns out some of the shorelines would still be around 14 meters, some would now be higher than 14 meters, and some would be lower. So we can start to piece together these sort of spatially variable records of past sea level to actually make sense and bring them together, narrow down those error bars and say, actually, this makes sense. We can understand this variability because of the processes that have gone on since those ice sheets were smaller. So there's a lot of sea level stuff in here. There's not many sea level people in the room, but go and talk to sea level colleagues. This is really good stuff. So hopefully there's a little bit for everyone in there. I'm aware there's some seismologists, there's some deep earth people in the room. So we do go bigger scale in GIA. We can start to think about deep mantle viscosity. And that's because GIA actually changes the rotational state of the whole of the solid Earth. And if we think about changes to the obliquity of the Earth and changes in the orientation of the rotation pole, these processes, the timescale of these processes, depend on deep Earth sort of viscosity. So what we've got here is a hypothetical Earth, slightly elliptical. This ice sheet, I think it appears from outer space. So we'll ignore the fact that mass has to come from somewhere. But if you can imagine an ice sheet suddenly appears on the Earth, you're going to kick out the rotation axis of the solid Earth. And so gradually over time, there's a response to this change in the rotation axis. The whole solid Earth behaves as a viscous fluid on long time scales, and we can see a change in the shape and the obliquity of the Earth and the rotational state. And so these sort of measurements relate to GIA, post-glacial rebound, the redistribution of surface mass, but they tell us about viscosities very deep in the Earth. Now there's one more area that I'll touch on before we end up in Antarctica, but we're heading to Antarctica. And it's thinking about how GIA affects ice sheet dynamics. I'm going to get you all interested in ice sheet modelling now. So I've drawn this figure here with an ice sheet sitting out on the continent. It's nowhere near the ocean. Now actually in Antarctica, this picture is wrong. This is the edge of the ice sheet in Antarctica. So it touches the ocean. It's not sitting on the land somewhere. It extends right out into the ocean. And it's a nice little diagram here. So what happens is in the interior of Antarctica, the bathymetry, so the land is actually below sea level. If we took away the ice sheet across a lot of Antarctica, you'd see land below sea level. But the ice is so thick that we have grounded ice. It's thick enough that it's not floating. But it flows as a sort of gravitationally spreading fluid, as a viscous fluid, and eventually the ice gets thin enough as it spreads that it starts to float because the water depth becomes great enough that it's no longer grounded, and you get these floating ice shelves on the edge of the ice sheet. Now the reason for showing this diagram is to point out this location here, which is the grounding line. So when we're thinking about the health of an ice sheet, we think about is it losing or gaining mass? So we think about how much does it snow each year, and how much ice flows across the grounding line into the ocean. So how much are we gaining versus losing ice mass? And if we have a positive or negative number, we can work out if the ice sheet's growing or shrinking. Now it turns out that the flux rate across the grounding line, so the rate at which we lose ice into the ocean, depends on the water depth at this point. So the thickness depends on the water depth because we're thinking about Archimedes' principle. But you can imagine that as sea level rises and falls, you actually kick the location of this grounding line position backwards and forwards. And if it were to retreat backwards, we have thicker ice. And there's a positive relationship, there's a linear relationship, well, it's not linear relationship, but thicker ice will lead to a greater flux of ice off the ice sheet. This is a little bit clearer in this upper figure here. So I mentioned that a lot of Antarctica, the land is below sea level, and in fact it slopes downwards towards the centre of continent. So it gets deeper and deeper towards the centre of the ice sheet. And we call this a reverse slope bed. So here we have a grounding line. You can imagine the situation, if we kick sea level up a little bit, this grounding line will start to float. So these are time slices going paler in time. And the grounding line steps back a little bit into deeper water. Now deeper water means thicker ice. Thicker ice means a greater flux. If we don't have any more snowfall, then we start to get a net loss of ice across the grounding line. Now this is a problem here with this reverse grounding line, because if we're losing ice, we're going to thin the ice sheet, it's going to start to float, and the grounding line steps ever further back into deep water. This is an unstable situation. And a lot of studies now, they're running models looking at the unstable loss of West Antarctica. And this is the processes that they're modelling. But actually, GIA is a bit of a saviour here. So there are these two processes that kick back against this in GIA. So as we start to lose mass and thin the ice sheet, the land underneath will rebound slightly. So we're losing mass, the land comes upwards. Also, the shape of the sea surface will change, going back to that diagram earlier. So the ocean surface will drop a little bit. So remember that as we lose mass in the near field of an ice sheet, we actually get a drop in sea level due to these GIA feedbacks. So if the slope is not too steep, then these feedback processes can actually help to damp that change we see as the grounding line retreats, and actually give up a stable situation here. So there's a whole area of research I'm not going to talk about today. So typically we take an ice sheet, we put it on the Earth, we calculate the deformation of the Earth, and we get our outputs, we get present day uplift rates. Now there's a sort of feedback here, and actually people are now running ice sheet models and GIA models that are coupled together. So rather than prescribing the ice sheet change, what they're saying is that, okay, let's assume the ice sheet changes a little bit, but thinking about these feedbacks, how will that influence future ice sheet change in tandem with the solid Earth change? So hopefully there should be something for everyone here now. And I will take you down to Antarctica. So there's two unknowns in the models that I run. I need to know the ice sheet history, and I need to know the rheology of the solid Earth. But actually, an overarching question of all my research is what's going on right now. This is Antarctica here. What's going on with this ice sheet? Now, we measure changes in the ice sheet using satellites. It's a massive ice sheet. It's very difficult to go across and measure the thickness of ice every year in every location. So the satellite data that we use looks at things like the change in the volume of the ice sheet, change in the elevation of the upper surface of the ice sheet, and also the change in the mass of the ice sheet. So we look at the gravitational field to see a change in the mass of the ice sheet. Now, that's all very well, but GIA adds a complication here. So this is where we get this feedback between processes associated with past changes in the ice sheet and processes associated with present changes. So you can imagine that as we look at a change in the elevation of the upper surface of the ice sheet, the land underneath is also rebounding. And it might be rebounding because we're losing mass, or it might be rebounding because of past changes. So what we have to do is take out this signal due to GIA to actually interpret these satellite observations. So heading down to Antarctica, this is the northern Antarctic Peninsula. It's a very mountainous area of Antarctica. So thinking about these two unknowns, the first thing I have to come up with is the history of the ice sheet. And this is where the fact that I sit in a geography department is fantastically useful. I have colleagues whose careers are based around reconstructing the shape of past ice sheets. And they look at the positions of moraines, the age of those moraines. They use cosmogenic exposure dating, so you can look at these mountainsides and work out when they were covered with ice and when they've been exposed to the atmosphere again. So I can build up these models. The data are sparse, and we have massive areas of the ice sheet where we have no information, and I fill that with some physics. So what I do is I run an ice sheet model, and I put in there the physics of ice flow, and we try and match these constraints, but also reconstruct the shape of the ice sheet in between. So I place this on the solid Earth. I run my GIA model. I calculate the solid Earth deformation, change in the shape of the sea level. But my other unknown was the rheology of the Earth. Now, it's quite difficult to constrain the rheology of the Earth. So what we do in Antarctica is we actually look at records of solid Earth rebound. Now, one way we could do this is to place GPS receivers here and look at the rebound in the present day. But there's this complicated signal. That rebound is due to past and present change. And we're trying to understand both of those. So what we actually look for is past records of solid Earth deformation. You can get that from sea level change. So we might find shorelines preserved along this coastline, but up at 20 meters above sea level now. So they tell us that there's some component of solid Earth rebound. After the ice sheet was much bigger and pushed it down, this land has now uplifted, and the shoreline, which was previously cut across the land here, is now up in the landscape somewhere. Now, obviously, the sea level changes as well, so it's not just solid Earth deformation that's being recorded when we see these shorelines. So you run it through a model, you think about the solid Earth and the change in the sea level, and you come up with a rheology for the mantle, which fits all the data. Now, I'm going to head off in a slightly philosophical tangent here. How do I know my model's right? I'm completely guilty of this first cartoon here, where the man's saying, get all the information you can, and we'll think of a use for it later. There are so many processes going on in GIA to do with the solid Earth, the ice sheets, the oceans. When I go to AGU, it's chaos because there are so many sessions that I want to go to. And I'm always on the lookout for all sorts of data that constrain my models. So it's a really fun field to work in. But we also have biases in the field data. So this is where, as a mathematician, I get a little bit uncomfortable with what's going on. But we have examples. So if we have a shoreline, evidence of a beach preserved in the landscape, how do we know whether the sea level, that was the sort of mean height of sea level at that time, we can date material in the beach, or was it a storm? Was it a really freaky storm that caused this beach to be formed 5 meters above mean sea level? So we have these biases in the field data that we need to think very carefully about, so that when we tune the model, do we actually tune the model really tightly to the data, or do we give it a little bit of flexibility? At what point do we say, okay, that's a good enough fit, given the biases and the uncertainty we have in the field data? And that sort of links to the past, the last point I have here, in that traditionally when we run a GIA model, people want to know, what's the present day uplift rate across Scandinavia or Antarctica, what's your model say? And I'll give them a single output, a map of uplift rates, and I say, that's it, that's the answer. But that's not really good enough these days, as we're thinking about uncertainty and change the data. So there's been sort of a big shift in the field in the last 5-10 years, sort of running ensemble models, looking at whole suites of solutions and trying to tease out the likely behavior of these systems rather than just nailing it down to a single answer. So it's a little bit difficult to know if my modeling is right, but this is one of the key results that I came up with a couple of years ago. So what you're looking at here is a prediction of uplift rates across Antarctica, and this is solid Earth rebound, due to past changes in the thickness of the ice sheet. So these red through to blue colours indicate areas where we think the land's rebounding very, very quickly in the present day, and actually there are areas where we think the land's subsiding. Now the reason for this sort of pattern, for those who aren't familiar with Antarctica, is because at the present, the grounding line, the point at which the ice starts floating, is at the back of these sort of big embayments. But during the last glacial maximum, the ice sheet was actually much bigger, so we had grounded ice out to around this sort of region, and probably around here. So there's certain areas in Antarctica where the ice sheet was much bigger, and it's since retreated, and that's why we predict the rebound in these particular areas. Now the dots you see on here, these are GPS measurements. So these are measurements of present day rebound. They've been corrected for the rebound due to contemporary ice loss. So there's a slight circular argument in there, but we can independently constrain present day ice loss. We correct for that. And these dots should match my model predictions. And they don't. They really don't up here in West Antarctica along the Antarctic Peninsula. And this was quite disappointing to me. I'd put a lot of effort into trying to reconstruct the shape of the ice sheets, forced by climate change, sort of the changes in temperature and snowfall through time. It's constrained to fit evidence for the shape of the ice sheet, but I didn't fit the rebound at the present day. So we're over-predicting uplift across a lot of West Antarctica, and it's very difficult to validate these models. But the length scales across here are massive, so we're filling a lot of gaps with physics here. And there's a lot of assumptions. And the way I tuned the ice sheet was to fit to field extents and use physics. But the way I tuned the other unknown, the Earth rheology, was to actually look at these sea level records. And the question I asked was, okay, let's try a particular upper mantle viscosity, run it through the model. What sea level change would I expect? Does it match the records, yes or no? And I found that I couldn't come up with a single mantle viscosity which fit all the data. So there's sea level records at various points around the continent, and I couldn't fit all of these records with a single mantle viscosity. But in the model I was running back in 2012, I could only choose one mantle viscosity. It was quite a simple model. So what I wanted to do was I wanted to run a more complex model for a start, to be able to actually define different mantle viscosities in different locations, and I needed an independent way of constraining those. So this is when I started talking to seismologists. So this is a beautiful map. This is the bathymetry on Antarctica. So remember, I mentioned that if you took the ice away, you'd actually end up with land below sea level in many regions. And so this, across West Antarctica, the land's 2,000 meters under sea level here. It's an amazing data set that we now have across this region. But the reason for showing this is to point out that Antarctica is not a big, stable craton with sort of a nice homogeneous sort of geology under there. We have this, so we were looking at this rifting zone over here yesterday. So this area of Antarctica, East Antarctica, is very, very old. It's thought to have a very thick lithosphere, quite a cold upper mantle in this region. But over in the west, this is a big rift zone. We have a lot of present-day magmatism here. There's an old subduction zone across this area. So it's really quite a diverse continent geologically. And we're quite fortunate. There's quite a lot of data coming out right now due to international efforts to actually understand what's underneath Antarctica. So this is a study from Mejan An. He had 2 papers out last year. using seismic arrays across Antarctica to reconstruct lithospheric thickness and also seismic velocities at different depths in the mantle. So I won't dwell on this, it's not my area of research, but I welcome feedback on how I interpret these data and sort of think about the uncertainties there might be in here. But what I do is I use this information to build a more complicated model of the Earth. So more recently I've been using a finite element model. So what I do is I divide the Earth into, they're not triangular, they're sort of rectangular blocks. I have a 2-degree resolution at the surface, and I have a series of concentric shells. And in each of these square Lego blocks, I can define the rheological properties of that block. And each block can have different rheological properties. And what we do is we think about the strain rate that you might get depending on the properties of each of those blocks as we load it with ice and ocean loading through time. This is the only equation there's 2 equations. So just to highlight the sort of things that my model depends on is things like the grain size in the mantle, the water content in the mantle, if there's a melt content in the mantle, and also we use temperature. And we feed information on all of these from a range of sort of experimental data and seismic tomography into this equation which relates the strain rate to the stress. So the stress is related to the surface loading. We have a surface loading history, and given these parameters, we can work out the strain rate through time. We also, it's an interesting point here, so in GIA models traditionally, people define a viscosity. We traditionally use a Maxwell rheology. In the model that I'm using now, we have a power law rheology. And actually what that means, it's quite interesting, I don't define the viscosity anywhere, but it depends on the stress. So Q folds in the stress here, and B is sort of to do with these parameters. But all you need to know here is that the viscosity depends on the forcing that is applied. So actually, what we will find is that across Antarctica, where we know that there's very different lithospheric thickness, different mantle, velocity, seismic velocity perturbations, which we might infer as different rheology, is we're solving for this rheology, we're not defining it. And we'll actually get different viscosity values if we assume a different forcing history. So if we assume a different surface loading history, the model pulls it out. So there's sort of interesting discussions going on about how you treat the rheology and solve for it in these situations. At the moment, my model only has lateral variations associated with temperature, which we pull out of seismic velocity perturbations. But there is the potential for there to be lateral variations associated with different grain sizes and water content across the continent. So this is a quick sort of recipe if you want to run your own 3D Earth GIA model. This is what you need. So I use global tomographic models, but I also use these sort of regional models of seismic velocity. And I convert that to an absolute temperature. And that feeds into that creep law we saw in the previous slide. I assume some water content and grain size parameters. That defines that finite element mesh, the properties. I load it with an ice history. I throw it into a GIA model. It solves for the sea level change, that gravitationally consistent sea level change. And I can produce outputs like present day uplift rates and sea level change through time. So we can see here, Antarctica, it's sort of divided West Antarctica and East Antarctica into these 2 very different domains. And the area where my model wasn't fitting towards before was West Antarctica, so I was over-predicting the present day uplift rates. But you can see from these, this is S-wave velocities, that we have these slower velocities over in West Antarctica, so it's sort of a hotter area, probably a lower viscosity. And if you have a lower viscosity, then you have a faster relaxation time. So these are the results that you get if I actually use a more complex Earth model. So this was the plot we saw earlier with uplift rates, and with very fast uplift rates across West Antarctica. I'm using the same forcing, so I'm using the same history of ice sheet change here, but I get very different results to what I think the present day uplift rates are. And that's because over West Antarctica, I have a much lower viscosity here. So what's happened is actually a lot of the rebound, which is still going on here, has now decayed because we have shorter relaxation times under West Antarctica. And this has quite important implications actually for determining the present day state of the ice sheet. So if you remember, whenever we look at, say, a classic example of how to look at this change in the mass of the Antarctic ice sheet is to use GRACE data. So we look at the shape of the gravitational field and how it changes through time, and we can start thinking about how mass is moving around the surface of the Earth. Now, mass moves around because ice is melting and going into the ocean, but also if the land is rebounding and moving closer to the satellites, that looks like a mass increase. So what I have to do is actually take out a gravitational signal due to this rebound when I'm looking at the GRACE data, and what's left is a gravitational signal of ice mass change. Now, the gravitational signal associated with these two maps will be very, very different. So we're in the process of sort of really changing our idea of how quickly we think Antarctica is melting, because if we apply a smaller correction for the GIA component, this can change our estimates of how quickly Antarctica is melting. So we think our estimates give Antarctica melting is sort of between 50, maybe 60 gigatons per year. I'm just going to... Yeah, I'm not going to do the calculation, you can ask me that later. But we change our estimates by around sort of 8 to 10 gigatons. So it's a really significant change we get if we think that GIA looks like the panel on the right versus the panel on the left. But we need to verify this. Once again, I'm making assumptions here. I go back to that question of, is my model right? And one of the things I do is compare with other ways of understanding what the GIA signal is. I'm going to quickly run through what an empirical GIA model is. So we use two satellite data sets traditionally to look at the change in the mass of the ice sheet in Antarctica. We use gravitational data, and we use data that look at the altimetry of the elevation of the ice sheet. So basically the change in the volume of the ice sheet, which you have to convert to mass because we don't know what the density of the ice is. Now, with both these measurements, we need to correct for GIA. We need to correct for that rebound of the solid Earth. Now, there will be some correction. So these two measurements, they have a different sensitivity to GIA. So there will be some correction that we can apply to both those data sets where we actually come up with the same answer for ice mass change. It's an inversion process. And that's what these two plots on the right have done. So they basically take different satellite data sets which have a different dependence on GIA, and they invert for simultaneously the ice mass change and also the GIA signal across Antarctica of uplift here. Now, you may think I'm out of a job at this point because someone else has come up with GIA without all that complication that I run through. But these are very, very different. You can see differences in these plots, and there's a lot of assumptions and uncertainties that go into these as well. So I would argue that there's still a room for the forward modelling approach of GIA. But before, this is the one with the more complex Earth structure, and my rebound rates are now fitting quite well with these empirical estimates of what's going on across Antarctica, but except in this region over here. So in my model, I only think about ice sheet change up to around 2,000 years ago. It was sort of quite a crude temporal resolution of ice sheet change, and I don't consider anything that happened after that. I say, okay, it was done, and everything else we see is due to present day ice mass change. But you can see from these inversions, so these already account for present day ice mass change, but they're saying actually there's a big GIA component in this area. So what we're actually seeing is there's probably something gone on in certain areas of Antarctica. This is the Pine Island region, which is losing mass very quickly right now, but we don't know how long it's been losing mass for. And these are just hinting at perhaps it's been losing mass for more than the satellite era, more than the last 10 years, 20 years. Perhaps it's been losing ice for 100 years, 1,000 years. This is what this plot is starting to hint at. And really the key message here is that recent ice mass change across Antarctica will dominate the GIA signal in these areas where you have low viscosity, because there's not time for the signal to decay. And actually, recent ice mass change, so we're talking a couple of thousand years, 3,000 to 4,000 years, that's the time where I really don't know much about ice history across Antarctica at the moment. So I'll just show you a final study, just thinking about really nailing down numbers on mantle viscosity. We had this beautiful natural experiment which took place just over a decade ago in the Antarctic Peninsula. So this was a floating ice shelf which collapsed over the course of a month. Now it was floating, so it won't contribute net mass to the ocean. You won't change sea level. But what it was doing is it was holding back, these are steep glaciers in the mountains behind, it was holding the ice back. And as it collapsed, these glaciers started to flow much more quickly. So this is a change in the velocity across the front of Crane Glacier. It was previously flowing at about 1.5 meters per day, and it accelerated to flowing at over 5 meters per day. And this is a profile of the change in velocity. So because it didn't snow anymore, but the ice started flowing faster, we had a net mass loss. And we could quantify quite well how much ice was lost in the aftermath of this ice sheet collapsing. And we had a GPS, fortunately we had a GPS receiver. It's sort of over here in the sort of map scale of things. So not right next to the ice shelf, but it recorded the change in uplift. So the GPS, it was sort of kicking along, it was slightly rebounding due to past ice mass change. And as the ice shelf broke up, we saw this rapid change in the uplift rate recorded at this GPS receiver. And we had a PhD student at the time, Grace Neild, and she looked at this. She modelled the elastic response you'd expect due to the amount of ice that we started losing from 2002 onwards. And if you look at the elastic response, you get a change in rate that looks something like this red line here. She couldn't get anywhere near the change in rate that we actually observed with the GPS receivers. And up till now, in all our calculations, in all our corrections of GPS data, we'd assumed that present day ice mass loss just triggers an elastic response. So there's an elastic response to present loss, there's a viscous response to past loss. But what Grace showed is actually, she just tried removing 5 times the amount of mass, and that's the only time she got close to it. But what she showed is that actually you have to consider the viscous response to the ice that was lost in this region to get anywhere near the GPS rate. So this green dot is the GPS rate, which was recording around 12 millimeters per year. She got nowhere near it with the elastic modelling, and you have to invoke a viscous response. The only way you can get a fast viscous response is to have a very low mantle viscosity. So this is really the first time we managed to put some hard numbers, because we knew one of those 2 unknowns, ice history or earth rheology. We knew the ice loss that we had, and we could really start to pin down the earth rheology. Now, unfortunately, we don't lose massive amounts of ice every day, so we need to think of other ways to look at the earth structure under Antarctica. And this is just my final slide before the conclusions, and it just shows the massive advances we've made through geophysics, basically, just in the last decade. What you're looking at here is distribution of GPS receivers, which are circles, and seismometers, which are diamonds, across Antarctica. And there's been a big project funded on the US side called PoleNet, which has deployed a lot of these instruments. This is sort of the British bit of Antarctica, so a lot of these GPS receivers have been put out by British Antarctic Survey. But there's not really any diamonds in this area. So a couple of projects that I'm involved with. One is actually to deploy seismometers across this region of southern Antarctica, southern peninsula. This is collaboration with the Leeds project, led by Graham Stewart. And also we have a project up at Durham led by Mike Bentley to put some instruments in this big gap over here. So what we're looking at, this is why I was down there, we're looking at rebound, and we're putting seismometers out to try and image what's going on underneath Antarctica and nail down those properties of sort of what's the viscosity underneath there. So just to conclude, hopefully I've convinced you that GIA is interesting, whether you're a solid earth person, an ice sheet person, or a sea level person. And we actually learn a lot from model data misfits. So my modelling back from 2012 didn't fit the observations at all. Now I could have accused the data of being wrong, but we stepped back and we thought, what are we missing in the modelling here? It's a really fun way to make advances in science. It's not just an old phenomenon. People often think we had a big ice sheet in the past, it disappeared, and we've got relic rebound. But actually, in areas where we have low upper mantle viscosity, then quite recent changes are going to be causing the rebound that we see in the present day. And we don't always know what happened to the ice sheets in the relatively recent past. So I just leave you with the question, hopefully there's something in there that sparked your interest. So what can GIA do for you? Thank you. Yeah, we do. Good question, actually. Only if we're thinking about very long time scales. But so I showed the study looking at Pliocene sea levels. And we sort of got a first order answer. Well, I wasn't part of that study. They got a first order answer for how much higher mean sea level was at that time. But then some of the data that they looked at were actually from margins which, if you think about dynamic topography, have been warping on tens of meters over those sort of timescales. So as we look back over millions of years, we're trying to piece together these records of sea level, these shorelines. But absolutely, it's an emerging field. There's just sort of one group that's really looking at it. But you have to correct for dynamic topography as well when we're looking at these. That's a bit of a long time scale for me. But yeah, good question. Yeah, so, yeah, absolutely. So my approach is a little bit cautious. So we don't make the step from seismic velocity perturbations all the way through to viscosity. We let the forcing come up with that themselves. Other groups are using conversions and are coming up with similar values of sort of 10 to the 18, 10 to the 19. But it's just, I tried to limit the number of assumptions that I got to and just let the physics deal with it at some point. And it's very different across East Antarctica. We don't get values anything like that. But there's areas like the peninsula, Patagonia, Iceland, where those sort of viscosities are looking realistic. It might be. So there's two studies that have come out in the last year, actually. So most studies that collapse West Antarctica, they have either a fixed solid Earth or sort of a standard rheology. And they get rapid grounding line retreat due to the marine ice sheet instability. But these two models, which come from the GIA field, said actually, there's a weak viscosity here. The rebound is going to be faster than these standard Earth models. And they found scenarios where it could prevent the complete retreat, from the Ross Sea right through to the Weddell Sea. Until we can pin down the viscosities and the rate of feedback, so timescales is difficult, but there's certainly examples from modelling which have shown that you can mitigate the retreat a lot because of just in West Antarctica. If this happened in East Antarctica, it's stronger. The rebound feedback won't be as large, so possibly problems still in East Antarctica. So the GRACE data give us typically a monthly time series. Some, I don't deal with the processing, but some groups sort of deal with the sort of quite raw data, and they come up with 2 weekly intervals. But it's a monthly time series of mass change. So a nice high resolution. The GRACE data are fantastic. You can start pulling out, seasonal water mass change and atmospheric changes. It's a beautiful time series. But the problem is that it just measures everything. It sort of measures mass movement in the whole Earth. And so it's up to people in different fields to say, actually, this is the bit due to ocean density changes. This is the bit due to the solid Earth. But yeah, a beautiful time series on a good time scale as well. Yeah, so we use the temperature gradient. There's a page in a book by Karato, and I use the values in there, and I don't know the assumptions that sit behind that. So that's, Graham's legged it out of here now. I would have asked him, but there are uncertainties in that calculation. But what I really want is I need an absolute temperature, but it's all based on a perturbation. So I assume a particular one-dimensional geotherm, and I'm just thinking about how far away, what's the magnitude of the perturbation in a particular location in the mantle. We assume that the whole of the perturbation that we see is due to temperature differences, but there will be compositional differences which will have some effect in there. At the moment, I assume no melt anywhere, so that parameter set to 0. That's reasonable, except in a few areas of West Antarctica, but it's quite small-scale melt. So the scale that I'm modelling on, I probably don't need to resolve that. One thing I've recently found, though, is that I do have to assume a wetter mantle towards the peninsula, where we have an old subduction zone. So I'm going to start to build in spatial variations in water content in the mantle, which we're going to need to explain some of the observations. So the Scandinavian ice sheet disappeared by around 10,000, 9,000, 8,000 years ago, and it's still going up at a centimetre a year today. So, at 8,000 years ago, it was going up much faster, and that's decayed. Yeah, so it's an exponential decay. So, yeah, it's sort of tens of thousands of years at this sort of the magnitude that we can measure today with GPS. So we have a problem in glacial cycles because you never reset the clock. We try and look to the last interglacial to understand what sea levels were then, because it was warmer, but it's all just part of this transient process. So you need to think about how long was an interglacial, you know, how close did we get to equilibrium before it started kicking off again. Yeah, we do. The most beautiful record comes from Scandinavia, and there's sort of a profile along a river, basically, and it can go back, I'd be guessing if I put numbers on it, but it's the point at which the ice disappeared, and you let the land be next to the ocean. So we have sort of back 8, 9, 10,000 year record, and it's a beautiful exponential curve, so you can look at that early rate of rebound that was going on there. That's really, really rare. We struggle to go back in time in many locations, partly because the ice still covered it. That's a big problem. So we don't always know the maximum depression because the ice has sort of covered it up and we don't know what was there. But yeah, trying to get as many time periods as possible to get that relaxation time is really important.
Any more questions? May I say if we can rank Pippa one more time?